Okay, let's unpack this. Forget your everyday mysteries. We're diving into the ultimate intellectual adventure, the hunt for a single theory that explains everything in the universe.
A theory of everything, the TOEI.
Exactly. It's sort of the Everest of physics, right?
Mhm.
And we've got our base camp set up with some really interesting excerpts from the Wikipedia page on this very concept of our mission today to give you a clear picture of what a TOEI is, why it's the holy grail for physicists and the big ideas and, roadblocks involved, all without getting lost in a black hole of jargon.
Yeah, and what's striking right from the start is that this longing for a unified explanation, it isn't some modern invention.
Oh, really?
No, even way back in Babylonian astronomy, you see people trying to connect the dots,
Right.
between the heavens and earth, searching for some kind of grand cosmic order.
Finding patterns.
Exactly. And Hindu cosmology, with its mind-bending cycles of creation and destruction spanning these just unfathomable timescales, it echoes some of the big questions we're still asking about the universe's origins and fate.
Absolutely. It's like humanity has always had this nagging feeling that there's a deeper underlying harmony to it all.
Hmm.
And it wasn't just about observing. The ancient Greek and Indian atomists took a huge leap, didn't they? Suggesting all the diverse stuff around us is made of just one fundamental ingredient, atoms.
Yeah, atoms interacting in different ways. Talk about a reductionist vision. Even back then.
Right. And sort of laying the groundwork.
Precisely. And when you think about Archimedes, with his focus on logical deduction from basic principles,
Axioms, yeah.
you see the very spirit of what a theory of everything aims to be. A set of fundamental axioms from which everything else in physics can be, derived. That methodical approach is really a cornerstone.
Okay, so fast forward a bit,
Yeah.
the 17th century.
Right, and you've got this mechanical worldview taking hold. The idea was that everything could be explained by tiny particles basically bumping into each other.
Like little billiard balls.
Kind of, yeah. It's obviously much simpler than our current understanding, but you can see that same drive find a single mechanical explanation for all physical phenomena.
And then came Newton.
Ah, yes. The pivotal moment in that century, without a doubt. His law of universal gravitation, that was the first monumental unification in physics,
He showed that the force pulling an apple to the ground.
is the very same force that governs the orbits of planets.
And the tides, too.
And the tides,
Yeah.
yeah. It was the first time seemingly unrelated phenomena were brought under one elegant mathematical umbrella. Just what a conceptual leap.
Mind-blowing is right. And then you get Laplace in the early 1800s imagining this mind so powerful it could know the position and momentum of every particle.
And predict the entire future, a completely deterministic universe governed by these unified laws.
That sounds incredible.
Laplace's vision really captured the allure, the attraction of a complete unified framework. But yeah, if we connect this to the bigger picture, modern physics has revealed a much more nuanced reality. Quantum mechanics introduced inherent unpredictability.
The fuzziness at the small scale.
Exactly. And chaos theory showed us that even in classical systems, tiny changes in starting conditions can make long-term prediction basically impossible.
So any modern theory of everything has to deal with that, with
Yeah.
probability and, chaos.
Absolutely. It's baked in now.
And the unification story doesn't stop with Newton. The 19th century delivered the second major breakthrough.
Maxwell. Electromagnetism.
Right. He showed electricity and magnetism weren't separate forces.
No, just different aspects of a single electromagnetic field. Plus, it turns out that many of the everyday forces we experience, feeling solid objects, the stretch of a spring, are ultimately manifestations of these electromagnetic interactions at the atomic level.
Wow. Okay. So much comes down to that.
It really does. And what's fascinating is that even as these incredible unifications were unfolding, the quest for something even more fundamental continued. Faraday, mid-19th century.
Yeah.
He was already exploring potential links between gravity and electromagnetism. Didn't quite work out for him, but the idea was there.
He was ahead of his time.
Definitely. And then, dawn of the 20th century, Hilbert's sixth problem explicitly challenged mathematicians and physicists to find a complete set of axioms for all of physics.
Like a direct call for a theory of everything.
Pretty much, yeah. A clear precursor to the modern pursuit.
So the 20th century arrives, bringing with it quantum mechanics, late 1920s.
And quantum mechanics was spectacularly successful, explaining the microscopic world how chemical bonds form.
And Dirac famously declared that the underlying laws for a large part of physics and chemistry were basically known.
He did. which sounds tantalizingly close to a toe, doesn't it?
He really does.
But this raises a crucial point. What do we actually mean by a theory of everything? Dirac's statement, while incredibly optimistic about quantum mechanics in its domain.
It didn't include gravity.
Exactly. It didn't include gravity. And, as we soon discovered, the strong and weak nuclear forces added significant complexity.
Right, the picture got bigger.
Yeah. Quantum mechanics was a triumph for understanding the non-gravitational forces at small scales, but the challenge of incorporating gravity remained this huge unresolved issue.
Speaking of gravity,
Hmm.
Einstein. After general relativity in 1915, his main focus for, decades was this unified field theory.
That's right, combining gravity and electromagnetism.
But it's almost a bit sad when you realize, as the Wikipedia entry points out, that the other two fundamental forces, the strong and weak forces, weren't even fully understood yet.
It's true. Einstein's unwavering dedication to this unified field theory is, well, it's a compelling chapter. He was deeply convinced of the fundamental unity.
But the rest of physics was kind of moving on.
In a way, yeah. The majority of the physics community was increasingly focused on the rapidly developing field of quantum mechanics, which took a very different approach. This divergence led to a degree of intellectual isolation for Einstein later on. Though it's worth remembering, figures like Nordstrom, Weil, Eddington, Hilbert, Kaluza, Klein, they were also exploring similar ideas around unification early on. Even extra spatial dimensions were being kicked around back then.
Kaluza Klein, right. But then the discovery of the strong and weak nuclear forces happened.
Yeah.
Suddenly Einstein's two-force problem became a four-force problem.
Absolutely. That must have significantly changed the unification landscape. A much bigger mountain to climb.
And another critical realization emerged, didn't it?
Yes. That any truly fundamental theory of everything would likely need to incorporate quantum mechanics from the very start.
I just hope it pops out later.
Right. Einstein had hoped quantum mechanics might somehow emerge as a consequence of a deeper classical deterministic theory like general relativity. But the prevailing view shifted. We need a quantum theory of gravity.
And that incompatibility between general relativity for the big stuff and quantum mechanics for the small stuff.
That became the central hurdle. Still is, really, the core problem in the quest for a toe.
Okay, so that brings us to modern physics. As the Wikipedia entry outlines, a TOE today is generally understood to be a theoretical framework that unifies all four fundamental interactions: gravity, strong, weak, and electromagnetic.
And ideally, it should also predict the properties of all the elementary particles we observe.
That's a monumental task. Just listing them is hard enough.
It is. And what's fascinating here is the conventional sequence of theories physicists have developed as sort of stepping stones towards this ultimate unification.
Like a roadmap.
Sort of. First, electroweak unification, late 1960s. Glashow, Weinberg, Salam.
Combining electromagnetism and the weak force.
Exactly. Showed there are two manifestations of a single underlying force at very high energies, around 100 GeV.
And this involves the Higgs mechanism, giving mass to the W and Z bosons.
Precisely. At lower energies, those weak force carriers get mass, making the weak force seem short-range and different from the long-range electromagnetic force. But fundamentally, at high energy, they're united.
Okay, step one. What's next?
Grand Unified Theories, or GUTs. These are more ambitious frameworks. They aim to merge the electroweak force with the strong nuclear force.
At even higher energies.
Oh yeah, way
Okay.
higher, around 10 to the 16 GeV. This implies a single electronuclear force governing all three non-gravitational interactions at those crazy scales.
Wow, an electronuclear force.
It's a compelling idea, right? Suggests a deeper symmetry. Now, the simplest versions of GUTs, they've faced experimental challenges, kind of ruled out. But the general concept persists, especially in supersymmetric GUTs. These more elaborate theories might also explain things like dark matter or cosmic inflation.
Things beyond the standard model.
Exactly. But even GUTs are generally thought of as effective field theories, like low energy approximations of something even more fundamental that kicks in at still higher energies, maybe fixing some technical issues like renormalization.
And the final step, the biggest hurdle.
Is gravity, bridging the gap between GUTs or even just the standard model and gravity, unifying them at the Planck energy around 10 to the 19 GeV.
An almost unimaginable energy scale.
Right. That's the main focus of quantum gravity research, and it's where our current theories just break down.
So the Wikipedia entry is clear. No accepted theory of quantum gravity. No TOE with actual observational evidence.
Not yet. And a complete toe might also shed light on other big mysteries, like What drove inflation? What is dark energy? What is dark matter? These huge cosmological questions.
So who are the frontrunners in this race? The page mentions string theory and M-theory.
Yeah, prominent candidates, especially since the mid-90s, work by Edward Witten and others. But as the entry notes, there's no widespread consensus. It's still very much debated.
What's the basic idea of string theory? It's not point particles anymore.
Right. It's a radical departure. Instead of points, the fundamental constituents are tiny vibrating strings, like Planck length size. Different vibrations correspond to different particles and forces.
Electrons, quarks, photons, all just different notes on a string.
That's the idea. It's incredibly elegant, mathematically, very ambitious.
And string theory needs extra dimensions, right? 6 or 7 more.
Famously, yes. In addition to our usual 3 space and 1 time. It sounds weird, but the article connects it back to the older Kaluza-Klein theory.
How so?
Well, the idea of extra dimensions isn't totally new. Kaluza and Klein realized back in the early 20th century that if you applied Einstein's general relativity to a hypothetical 5-dimensional universe, with 1 dimension curled up really tiny, the physics in the remaining 4 dimensions looked remarkably like regular general relativity plus Maxwell's electromagnetism.
Oh.
Yeah. String theory builds on that. It suggests a consistent quantum theory with gravity needs these extra dimensions curled up or compactified so we don't see them directly.
And this might explain why gravity is so weak compared to the other forces.
That's one potential explanation, yeah. Maybe gravity can leak into these extra dimensions while the other forces are stuck in our 4 dimensions. Addresses the hierarchy problem, possibly.
Okay, so what's kept researchers working on string theory? The article mentions some theoretical hints.
Yes, there are some compelling aspects. The way the standard model particles seem to fit into certain mathematical structures in string theory, like SO10 GUTs.
Okay.
Potential frameworks for understanding why there are 3 generations of fermions, explaining their mixing rates. It's also made progress on deep conceptual puzzles like the black hole information paradox, black hole entropy.
Right, and connections to other areas.
Yes, gauge string duality, or ADS-CFT. It's revealed surprising links between quantum field theories and string theories, giving new tools and insights for both. Very powerful stuff mathematically.
But there's a but, a big one. The string theory landscape.
Ah, yes, the elephant in the room. The Wikipedia entry mentions this truly staggering number, 10 to the 500, maybe more.
Of possible 4-dimensional universes, depending on how you curl up the extra dimensions.
Exactly. Each different compactification could lead to different physical laws, different fundamental constants in our low-energy universe.
So how do you find our universe in that haystack? How do you make testable predictions?
That's precisely the challenge. It's incredibly difficult. If there's so many possibilities, how do we know which one, if any, describes reality?
And this leads to the anthropic principle idea.
It does, yeah. It's a proposed but controversial way out. Maybe only a tiny fraction of these universes can support life. So the constants we see are just, because we're here to see them. We live in a suitable neighborhood.
That feels unsatisfying to some, doesn't it? Undermines the goal of predicting constants from first principles.
It does. Critics argue it makes string theory potentially unfalsifiable, less scientific in the traditional sense. It's a huge debate. But despite this, string theory is still a very active research area. People are trying to tackle these issues.
Okay. What about other approaches? Loop quantum gravity.
Right. The article mentions LQG as another significant direction. Its main goal is quantum gravity, not necessarily a full toe unifying everything, but it could be a key piece.
And it predicts the smallest possible length.
Yeah, that's a key feature. It quantizes spacetime itself, suggesting it might be granular, discrete at the Planck scale, no infinitely small distances.
Which is different from string theory's approach.
Fundamentally different, yes. No extra dimensions, no fundamental strings. It's about the quantum structure of space-time geometry.
And there's some recent claims about it potentially connecting to particle physics, like braids in space-time.
Some intriguing, though still speculative, ideas modeling first-generation fermions as complex braids in the quantum space-time fabric.
Wow, particles as literal knots in space.
Sort of, yeah. But the article adds important caveats. There's no fully derived Lagrangian yet showing how these braids interact, no proof they behave exactly like fermions or reproduce the standard model's forces and symmetries precisely.
So early days on that front.
Definitely. But they're using ideas from quantum computing to show these braids might be stable, and interpreting charge as a topological property is?
Well, it's interesting.
Any other attempts mentioned?
Briefly, yeah. Causal fermion systems, causal sets, mainly focus on quantum gravity too,
Yeah.
and the ER-EPR conjecture.
Entanglement equals wormholes.
Basically, yeah, a deep proposed connection between quantum entanglement and space-time geometry. Very mind-bending.
Okay, so with all these ideas floating around, why are there still arguments against even the possibility of finding a toe, philosophical roadblocks?
Yeah, the Wikipedia entry touches on this. One famous argument comes from Gödel's incompleteness theorems in math.
Right, the idea that any powerful enough consistent system has unprovable true statements. Exactly. Some thinkers, Jakey, Dyson, even Hawking later on, suggested this might mean any formal toe for physics would also be inherently incomplete. You couldn't prove everything from its axioms.
So a fundamental limit built into logic itself.
That's the argument. If the theory is powerful enough to describe arithmetic, which you'd assume a TOE needs to be, then it's subject to Gödel's limits, either inconsistent or incomplete.
But not everyone agrees this applies to physics.
No. There are counterarguments. Schmidhuber talks about limit computable universes where the rules might be simple and complete, even if behavior is complex. Others argue it depends on what you mean by a toe.
Just the fundamental rules.
Yeah.
Or predicting everything that happens.
Right. Is it the underlying code or the ability to run the entire simulation and understand every outcome? Most physicists seem to think Gödel doesn't stop us finding the fundamental rules. Like, knowing the rules of chess doesn't mean you can predict every possible game.
Okay. What other arguments against a TOE?
Well, there's the idea of fundamental limits in accuracy. Maybe our theories are always just approximations getting better and better, but never reaching some final truth. Einstein apparently thought along these lines sometimes.
Like the universe is just too complex, or our minds are too limited.
Could be. Maybe science is just an endless refinement, not a journey to a final destination.
And then there's the whole reductionism versus emergence debate.
Ah, yes. Is a toe the only fundamental law, with everything else emerging from it? That's reductionism.
Versus emergence, where laws of complex systems like thermodynamics or biology's natural selection are seen as equally fundamental in their own right.
Exactly. You can't necessarily derive the rules of, say, bird flocking behavior just from the equations of quantum chromodynamics, even though the birds are made of quarks and gluons. Emergent laws have their own validity. The Weinberg-Anderson debate is famous here.
So maybe a toe for particles and forces wouldn't actually be a theory of everything we care about.
That's the emergence perspective. It might not fully explain biology, consciousness, economics,
And finally, the practical problem. Impossibility of calculation.
Right. Weinberg's example. Calculating a projectile's path through turbulent air. Even if you had the TOE, solving the equations for all those air molecules would be basically impossible.
So what's the use of a theory you can't compute with for most real situations?
Well, Weinberg's counter is that our confidence comes from the theory working in simple, testable cases. If it works there, we trust the foundations, even if complex calculations are too hard. The real test is reconciling GR and quantum mechanics fundamentally, not calculating weather patterns perfectly.
Got it. So wrapping up, where do we stand today?
Well, the Wikipedia entry is pretty blunt. We don't currently have a candidate TOE that includes both the standard model and general relativity and can calculate fundamental constants.
Still searching.
Still searching. The hope is that ongoing experiments, particle accelerators like the LHC, dark matter searches, cosmic observations, will give us the crucial clues we're missing. We need more data to guide the theory.
Okay, so let's recap our deep dive into this ultimate quest. We've traced this long historical journey, right? From ancient pattern seeking to Newton and Maxwell's huge unifications.
Then the two pillars of modern physics, general relativity and quantum mechanics, and the massive challenge of making them work together.
We looked at the standard model and GUTs as important stepping stones, but still incomplete.
Yeah, and the leading contenders now, like string theory with its extra dimensions and landscape problem, and loop quantum gravity with its quantized spacetime, both fascinating, both facing big hurdles.
And we touched on those deep philosophical questions. Is a TOE even possible? Gödel's theorem, emergence, calculation limits.
It really covers a lot of ground, this quest.
It really does. Which leads to maybe a final thought for you, the listener. This whole endeavor, this relentless chase for one unifying description of reality.
Is the journey itself maybe more valuable than the destination, all the discoveries made along the way?
Or perhaps there are just fundamental limits to what we can understand. Maybe a truly unified theory will always be just out of reach.
It definitely makes you think about science, about knowledge, and well, our place in the whole cosmos, something to ponder.